Okay, today we're going to look at inverse trigonometric functions. So we're going to define inverse trigonometric functions, and we're going to evaluate expressions involving inverse trigonometric functions. So to start by defining the inverse trigonometric functions, I'm going to look at the inverse sine and the inverse cosine function. Okay, so before we can do this, we've got to remember what information we learned about inverse in algebra. And remember, if you're trying to find the inverse function, then you switch your domain and your ranges, or your x's and y's, and then you graph it. And also remember that if the original graph passes the horizontal line test, then it's a one-to-one function. And if it's one-to-one function, then it has a inverse function. Well, we'll notice here our graph of y equals sine of x does not pass the horizontal line test. And so its inverse looks like here on the right, and that is not a function. And that's not going to be acceptable because we need our equations to be functions to do all the operations we want to work with. So our solution to this problem was that we restrict the domain of y equals sine of x. And then we're going to, once we restrict that, then we're going to find its inverse, and we'll make it so that the inverse equation is a function. So we're going to restrict the domain of y equals sine of x to negative pi over 2 to pi over 2. So if I restrict it, what I've highlighted here is the restriction that we just talked about. That's approximately negative pi over 2 and to pi over 2. So this is what the graph of our restrictive y equals sine of x looks like. So I'm only looking at x values between negative pi over 2 to pi over 2. And then when I sketch it, now my inverse equation, when I switch my x's and y's, and here's the graph of the arc sine of x. And notice that our domain is from negative 1 to 1, and our range is from negative pi over 2 to pi over 2. And so that's very important. Always notice the restrictions of the trig functions. So likewise, we can restrict our cosine. Okay, so we can restrict our cosine function, which is from negative is less than equal to y, which is less than equal to x. And then when we have y is equal to the inverse cosine of x, our restrictions are our range is going to be, our domain is going to be from negative 1 to 1. And our range is going to be from 0 to pi inclusively. Wait, this should have been x, because I was talking about the cosine function, and I think I did the same mistake up here. So change these two. That should have been, the sine is limited from negative pi over 2 to pi over 2, but the restrictions of the inverse functions are with the y's, because this angle is our y on the inverse function. All right, so there are two notations that are accepted to use with inverse trig functions. The one I've used so far, which is kind of have this exponent of negative 1. Now, no, that's not the exponent of negative 1. It is read that y is the inverse sine of x. So we'd read this, y is equal to the inverse sine of x. Or another very common one you see would be y, and you mark arc sine of x, but you don't read it arc sine of x. It is read the angle whose sine is x. So either notation are acceptable. I change them up. I use both notations as I'm working. I personally like the angle whose sine is x better, but the calculators like the y is equal to the inverse of sine of x. So you need to be familiar with both of them. Okay, so in our first example today, we're going to find the exact value of the angle y is equal to the inverse sine of x, inverse sine of 1/2. So basically, first thing you want to always think about on these inverse trig functions is your restrictions. So remember that the inverse sine is restricted from negative pi over 2 to pi over 2. So all my answers have to fall in quadrants 1 and 4 when I'm listing angle 4 measurements as negatives, not positives. So I know I need to be in these two quadrants. So I look at these two quadrants and I ask, okay, which of these have a sign that is a positive value? And that would be in quadrant 1. So I know my answer has to be a quadrant 1 angle measurement. So I recall my unit circle, and I think about all my angles in quadrant 1 that have a sign that's equal to 1/2, and that is pi over 6, and that's your answer. All right, so now I want you to try it on your own and find the exact value of the arc cosine of the square root of 2 over 2. This time we're done with the arc cosine, so we have to think of our restrictions for the angle whose cosine is our angle whose cosine, and that restriction is between 0 and pi. And so for cosine, we're restricted to quadrants 1 and 2. So I have to say which of those quadrants have a cosine that is positive. That's quadrant 1. And what angle on a unit circle has a cosine of pi, a square root of 2 over 2? Well, that's pi over 4. That's your answer. So when you're evaluating inverse trigonometric functions, you must pay very, very close attention to your restrictions. These are key. Do not forget your restrictions. So here's an example where it starts making it important that you recognize restrictions. So I know that cosine is restrictions are between 0 and pi. So that means my answer has to be in either quadrant 1 or quadrant 2. And then which of these quadrants has a negative value? Well, that would be in quadrant 2. And so I need to find an angle that has a measure of negative square root of 3 over 2. Now, if you just remember your quadrant 1 on the unit circle, you can just find your reference angle here. So I know my reference angle would be pi over 6 because in quadrant 1, pi over 6 has a measurement of square root of 3 over 2. And so I know that'll be my reference angle here. So I got to find my original angle. But remember, in quadrant 2, your reference angle is equal to pi minus your original angle. And so this time I'm going to have pi over 6 is equal to pi, which I'll write as 6 pi over 6 minus theta. And now solve for theta. I'm going to add theta each side, and then I'm going to subtract pi over 6 from each side. And I get an answer of 5 pi over 6. Or you could remember this from unit circle, whichever one. So I have, my answer is 5 pi over 6. Let's start with our restrictions. Our restrictions of the inverse sine function is from negative pi over 2 to pi over 2. We are in quadrants 1 or quadrants 4. And then I ask myself which of these quadrants have a sign that is negative, and that would be quadrant 4. But I'm not going to write it as my quadrant 4 measurement. I'm going to write it as negative 1. So if I can just find my reference angle, which I know has to be pi over 4, because that gives us a sine of square root of 2 over 2. And then I just move that to quadrant 4 by negating it. I would say that my y here is equal to negative pi over 4, or theta equals negative pi over 4. I didn't tell what variable, or the function equals negative pi over 4. So now let's think back again. When you learned about inverse trigonometric functions in algebra, in college algebra and stuff, you found that two functions are tests if two functions are inverse functions or not is if I take f of g of x equals x, and I take g of f of x is equal to x. Well, this rule also applies to inverse trig functions. The key is just remember your restrictions. So sometimes you might have to rewrite it so that it fits our restrictions. But when like here, I have the angle whose sine of the sine of 7 pi over 4. So this is like f of g of x, and it should equal to x. So I have sine and arc sine. But we first have to deal with the restrictions of our inverse sine function. Remember, our restriction of inverse sine function has to be between negative pi over 2 and pi over 2. So you ask yourself, is the angle given, 7 pi over 4, between the negative pi over 2 and pi over 2? And the answer is no. 7 pi over 4 is not between these measurements. So to find an angle that's between these that have the same measurement, you have to go back to coterminal angles. So I need to find a coterminal angle for 7 pi over 4 that falls within my restrictions of the inverse sine function. So remember, to find coterminal angles, you just add or subtract 2 pi, which I'm going to write as 8 pi over 4, and I get negative pi over 4. That is within my restriction. So I'm going to rewrite the equation as the arc sine of the sine of negative pi over 4. And then the arc sine and sine functions kind of like cancel each other out, and you're left with just what's inside, the x inside, because of these are sine and arc sine. So my answer is negative pi over 4. Okay, so I notice I'm doing the inverse cosine and cosine. So this we'll look and see if this will work out. First thing I got to do is what is the restrictions of cosine, the arc cosine function? And that is between 0 and pi. So is negative 4 pi over 3 between 0 and pi? No, it is not. So I have to first find a coterminal angle whose angle is between 0 and pi. So I take negative 4 pi over 3 and I add 2 pi, which I'll write as 6 pi over 3. And that'll give us 2 pi over 3. And 2 pi over 3 is between 0 and pi. So I'm good to go. And so what I'm going to do here is I'm going to rewrite this equation as the cosine of its coterminal angle. And I can do that because coterminal angles have the same measurements. And then it's just simply 2 pi over 3. Now that we know how to work with sine and cosine inverse trig functions of sine and cosine, let's learn the other inverse trig functions. The operations are all the same. It's just that you need to know your restrictions and kind of what the graphs look like. So we're going to start with our inverse tangent function. So the domain of the inverse tangent function, or the angle whose tangent is x, would be all real numbers. Our range, our range is what we're going to look at when we find our restrictions, is we're going to be looking at our range. That's what our restrictions are. Is from negative pi over 2 to pi over 2, not including those endpoints. And the reason why we don't include those endpoints is because we have asymptotes at y equals negative pi over 2 and y equals pi over 2. And so here below it, you can see the graph of the inverse tangent function. Next, let's look at the inverse cotangent function. Its domain is also all real numbers. Its range or restrictions fall from 0 to pi, not including the 0, not including the pi. And the reason for that is our asymptotes of this function are at y equals 0 and y equals pi. So here you can see the graph of the arc tangent, or the inverse tangent function. So we have a nice smooth curve that goes forever and ever. So it has a domain of negative infinity to infinity, and then our two asymptotes at 0 and at y equals pi. Last two trigonometric functions are our secant, and its domain of our inverse secant function is x needs to be less than or equal to negative 1, or x is greater than or equal to 1, because remember, we're taking that sine function, that cosine function, and flipping it over. And our range, our restrictions, are going to be 0 is less than y, which is less than pi, but y cannot be pi over 2. And that's because our asymptote is at pi over 2. So here is what the inverse secant graph looks like. You have cursor stopping at x equals negative 1, and then starting back at x equals 1, you have this another curve that goes up and over, approaching your asymptote at y equals pi over 2. And our last trigonometric function, the inverse cosecant graph, has a domain also from x is less than or equal to negative 1, or from x is greater than or equal to 1. The range or restrictions for this function is from negative pi over 2 is less than y, which is less than pi over 2, but y cannot be 0, because our asymptote for our inverse cosecant graph is at y equals 0. So here's our graph. We go until x equals negative 1, stop, okay, and then we start back at x equals 1. Both of these sides are approaching the asymptote of y equals 0. All right, now let's try some examples using these other trigonometric graphs. So I'm going to start with our inverse tangent function at negative square root of 3 over 3. So I'm looking at inverse tangent. So as always, think of your restrictions. What was our restrictions for tangent? It was from negative pi over 2 is less than y, which is less than pi over 2. So I'm in quadrant 1 and quadrant 4, and then ask yourself, okay, which of these quadrants has a tangent that is negative? And that would be quadrant 4. So I'm going to write it as the negative theta instead of going all the way around the circle. So we'll write it as a negative angle measurement. So I got to figure out my reference angle, theta. So we're going to find a reference to angle theta. So in quadrant 1, we got to figure out which angle has a tangent of square root of 3 over 2. And so if I think about that, I'm thinking theta or maybe pi over 6. Because we have the point square root of 3 over 2 and 1/2. And remember, tangent is sine over cosine. So that's going to be 1/2 over square root of 3 over 2. And if I flip that bottom fraction and multiply, I get square root of 3 over 3. But I don't want it in quadrant 1. I want it in quadrant 4. So that means it needs to negate it. And so theta, my answer, is going to be, so our answer is going to be negative pi over 6. The angle whose cosecant is negative pi over 2. So what's the restriction to the inverse cosecant graph? That's from negative pi over 2 is less than y, which is less than pi over 2, such that y cannot be 0. So I am again in quadrants 1 and quadrants 4. But I want a negative cosecant, and a negative cosecant occurs only in quadrant 4. So I know my answer is going to be in quadrant 4 here. So I got to figure out when is my cosecant equal to pi over 2. So deal with quadrant 1 first. So my cosecant of negative pi over 4 gives us negative square root of 2. Okay, because I know that the cosecant of pi over 4 is square root of 2. And so my answer is negative pi over 4. Now, so far, we've only done with angles in the unit circle. But what if we wanted to find any angle measurement, some angle that's not on the unit circle? And then we have to refer back to right triangle trig, or sometimes your trigonometric identities. So if I wanted to evaluate the sine of the angle whose cosine is negative 3/5, I first look at which one's our inverse trig function. So we have the inverse of the cosine function. So we find the restrictions to that function. And remember, the restriction is between 0 and pi inclusively. So I therefore say, okay, I have to be in quadrant 1 and quadrant 2. And I figure out which of these quadrants gives us a negative value, because we're looking at negative 3/5, and that would be quadrant 2. And so I draw an angle in quadrant 2, and then I make a right triangle out of this. And there's my theta that I'm going to look at. Now, since my angle whose cosine is equal to negative 3/5, I notice that my adjacent side must be negative 3. So our arc cosine is equal to 3/5. So I'm going to make that equal to y. So that means cosine of y is equal to negative 3/5. Oh, better thought. Let's use theta instead of y, this case, because I'll use y up there, and that represents something else with my restriction. So cosine of theta is equal to negative 3/5. And I recall that cosine is adjacent over hypotenuse, adjacent over hypotenuse. And so labeling my right triangle, my adjacent side would be negative 3, my hypotenuse would be 5. And so in order to find sine, I need to find my opposite side. So I'll label that as x. And then I remember that x squared plus y squared is equal to r squared. And so x squared is equal to 25 minus 9. So x squared is equal to 16, and that makes our x plus or minus 4. But in this quadrant, our y's are positive, so I'm going to write x as positive 4. And so now I can rewrite our original equation, the sine of the arc cosine of negative 3/5. I can replace the arc cosine of negative 3/5 with theta, because I said that's what they equal to. And I can just rewrite this as the sine of theta. And sine of theta, according to my diagram, would be opposite over hypotenuse, and our opposite side is 4, our hypotenuse is 5, so my answer to the original equation is 4/5. Okay, you're going to evaluate the tangent of the arc cosine of 2/3. So start with our inverse trig function and its restriction. So the restriction for the inverse of cosine is from 0 to pi. And so that tells us we need to be, again, in quadrants 1 or quadrants 2. And ask yourself which of these has a cosine that is positive. That would be quadrant 1. So I'm going to draw a right triangle in quadrant 1. Theta is going to be our central angle here. Now it was given that the arc cosine of 2/3, I'm going to let that equal theta. So therefore cosine of theta is going to be 2/3. And so cosine is adjacent over hypotenuse. So I'm going to label my right triangle's adjacent side with 2 and hypotenuse of 3. And then I'm going to find the missing side of my right triangle using our Pythagorean identity. So we got x squared plus 2 squared is equal to 3 squared. So x squared equals 9 minus 4. X squared equals 5. So x is equal to plus or minus the square root of 5. And since I'm in quadrant 1, I'm going to look with the positive. So x is going to be equal to positive square root of 5. So tangent is equal to the arc cosine of 2/3. I can rewrite that as tangent of theta. And theta is our remember, tangent is opposite over adjacent. And so theta would have to equal opposite, which would be square root of 5, over our adjacent, which is 2. I just realized I kept saying square root of 5, but I did not write my square root. So let's go ahead and put our square roots back in here. So that side is actually the square root of 5. I said it, I think, but I did not write it. Well, that's pretty much how you work with evaluate inverse trigonometric functions.